Okay, so let's talk about a few other types of commonly seen distributions. This one is called the log normal distribution. Okay, I mentioned this earlier. It's similar to a normal distribution, but it contains a much longer right tail. Okay, meaning the outliers or extreme values are much more common. Okay, so you can see here's my normal distribution, and here's an idealized version of a log normal distribution. You can see there are more instances of these high values. It's more likely to get these high values. Okay, now, as it turns out, many things are log normally distributed, and perhaps the most common one is income. Okay, so the income of incomes in virtually every country is log normally distributed. So here I have the distribution of income for the United States. You can see it's quite similar to this shape here. Here's the same data for the UK. Here's the income distribution in India. And then here's the global income distribution. All of these distributions are log normal. Okay. Even the salaries of CNU graduates are roughly distributed according to a log normal distribution. Okay. So now you might be thinking, so what's the big difference between a normal and a log normal distribution? And again, the answer is just the presence of those extreme values. Okay. So I mentioned earlier that height in human populations is distributed normally. So to get an idea of what a log normal distribution is, imagine that if instead heights were distributed log normally. Well, then we would live in a very different world, okay? The way it would look is basically there would be like a civilization of hobbits, okay? Of people who are here, who are pretty short, okay? And then occasionally, very occasionally, you would see a giant, like some guy who's like 10 feet tall. Okay, that's what a log normal distribution would look like if heights were distributed not log normally. Now, of course, heights are not distributed log normally, but incomes are. And this probably explains, our everyday experience with income, right? Usually at this point, if we were in a real classroom, I would ask people, how many people have ever met a millionaire? And probably, a few people would raise their hands. And then I would ask how many people have ever met a billionaire, and chances are nobody would raise their hand. Okay, so that's like these very uncommon but very rich outliers. Okay, that really is the characteristic of a log normal distribution. Okay, so you might be wondering, well, if a normal distribution arises from the sum of many independent factors, how does a log normal distribution arise? And the answer is a log normal distribution arises when many independent factors are multiplied together. Okay? And, okay, so you go, okay, so what's the difference between that? Well, so the idea here is that multiplication captures the idea that the total can be more than the sum of its parts. It implies basically a sort of synergy between the various factors that are involved in determining whatever factor is log normally distributed. Okay, and so now, okay, so let me use the income example. Okay, so if you think about it, many of the factors that determine somebody's income behave in this multiplicative way. Okay, so for example, consider two very important determinants of your level of income, right? First of all, your parents' wealth, and second of all, your years of education. Those are just two variables that influence your income a lot, right? Obviously, if you have more education, if you have, let's say, a bachelor's degree instead of an associate's degree, you're more likely to earn more money. And if your parents are better off, you're also more likely to be better off yourself, right? But my point is that these two factors, right, they don't act on your income or your wealth completely independently. They have a certain synergy with each other. One can make the effect of the other stronger. Okay? So for example, if your parents are better off, it enables you to potentially go to a more prestigious school. And if you do go to a more prestigious school, each year of your education is potentially more valuable, at least in the eyes of a potential employer. Okay. At the same time, a more educated person has more connections and might be in a better position to leverage money from their parents, such as an inheritance. Okay. If you inherit a lot of money from your parents, well, and let's say you went to Harvard Business School or something, chances are you got a lot of connections. So you can take that money you inherited and invest it somewhere good. So the point is each of these factors strengthens the other factor. And that's what I mean when I say these factors are multiplied together, right? When things are multiplied together, the effect of one strengthens the effect of the other. Okay. So, we can think about think about some hyper-rich individual within our society, right? Like, for example, who's the richest guy in society? Right now, it's Bill Gates, okay? So you can think of him as kind of like somebody who rolled a 6 on all of their dice, okay? Where those dice represent, intelligence and connections and access to education and all of the factors that might contribute towards a person becoming more wealthy, right? He rolled a 6 on all of those dice. And since all those factors synergize with each other, he ended up being, far more wealthy than individuals who maybe rolled a 6 on only a few of those categories. Okay? Okay, so that's a log normal distribution. Again, the most commonly log normally distributed variable, especially that we see in the social sciences, is income. Okay, so we'll talk about one more type of distribution, and that is a Pareto distribution. Okay, so a Pareto distribution is sort of like an even more extreme version of the log normal. It has even more of these very large outliers. Okay, and here are some examples. So the size of firms is distributed according to a Pareto distribution. The mass of planets is distributed according to a Pareto distribution. And then here are some salaries in Major League Baseball. These are also Pareto distributed. So, okay, so so to give you an idea of what this distribution is like. So again, once again, imagine that heights were distributed according to a Pareto distribution instead of a normal distribution. Well, what we would then see is we would basically see there would basically just be one giant amongst the civilization of ants. It's like an even more extreme version of the log normal. Okay. Okay. So now these are also very common. Pareto distributions are very common. So what generates a Pareto distribution? Well, the answer is Pareto distributions tend to arise when there is some sort of feedback cycle. Okay, so think of it as the rich getting richer and the poor getting poorer. When you have that type of situation, you tend to get a Pareto distribution. Okay, so let's consider a few examples of this. Let's consider first of all the mass of planets. Okay, so why is the mass of planets distributed log normally? Well, it turns out there's why are the mass of planets distributed according to a Pareto distribution? Well, for example, if you think about the planets in our solar system, at least, the largest planet is Jupiter, right? And Jupiter, as you may or may not know, is a giant planet. It's way, way larger than the size of Earth, right? Now, how did Jupiter get so big? Well, you got to understand, so when the planets were forming, they were basically all competing with one another to suck up the matter in the early solar system. Okay, and of course, the bigger a planet is, the more gravity it has, and so the more it's able to suck up matter, so the faster it grows. But then, as you grow bigger, your gravity only increases, and so your ability to suck up matter only increases. So again, it's this idea of sort of the rich getting richer. The biggest, the planets that sort of got to an early lead and started off kind of big only came to become much, much bigger than the ones who weren't so big in the beginning. Okay, so hopefully that gives you an idea of what I mean by this rich getting richer effect. Okay, now if you look at human affairs, fame very much behaves in the same way, right? If you're not famous, it's hard to get famous. But once you are famous, it's kind of easy to acquire even more fame because, well, you're already famous, right? So, so for example, the probably the most well-known example is the Mona Lisa, right? Why is the Mona Lisa is probably the most famous painting of all time. Why is the Mona Lisa so famous? Is it the most beautiful painting of all time? Is it the most noteworthy or the most, unusual or genre-defining painting of all time? Not necessarily. I mean, you look at it, it just looks like a portrait of a woman, right? And there could be, there's probably a million other portraits hanging in Italy somewhere that are somewhat resemble the Mona Lisa, right? The Mona Lisa is famous because it's famous, right? And so, okay, so now this explains actually, or it helps explain why salaries in Major League Baseball are distributed according to a Pareto distribution. You see, incomes in general are distributed not log normally, but among the rich or among celebrities in particular, income tends to be distributed according to a Pareto distribution. So, well, if you think about it, um, a celebrity's income is very much based on their level of fame, right? And obviously, once somebody is already famous, then, they can do a lot of things. They can go on TV. They can, sign a advertising contract with Nike. Like if you're not famous, Nike is never going to approach you to help sell their sneakers, right? But once you've attained a certain level of fame, then, you're getting all these product endorsements. And of course, those things only make you more famous because they're getting you out all over TV and all over the media and things like that. Okay, so this idea of the famous becoming even more famous, the rich becoming even more rich, that's what drives a Pareto distribution. Okay, so just as a quick recap then, different types of random processes, they create these different distributions, okay? And therefore we can understand a lot of what causes a certain phenomenon by examining its distribution, okay? And a tool for doing that, okay, a way that we can do that is by examining the histogram corresponding to those distributions. And then we talked about these three common types of distributions. Okay, so in the next portion, we're going to briefly look at some examples of this in our own survey data. And I'm going to ask you to work with that on the homework. So you definitely want to have a look at that, okay? And same thing with some other data. We're basically going to go look at some data sets and find some examples of these different kinds of distributions.